Hello everyone, myself V. Krishnaveni, working as assistant professor in the Department of Physics from Marri Laxman Reddy Institute of Technology and Management. So as of now, I completed 3 modules, that is Applied Physics, Quantum Physics and Solids. So till now I have completed 3 modules from this. This is the 4th module. So in this I am going to explain about the Schrodinger time independent wave equation and physical significance of wave function. So let us go for the PPT now. So Schrodinger time independent wave equation. So here Schrodinger in the year 1926 was derived equation for the wave, that is matter wave. The material particle has some wave equation. That wave equation was derived by the Schrodinger in the year 1926. For this, he has taken a material particle, that is electron, which is moving along x direction, having the velocity v, position x and time t. So here the wave function was described by the Schrodinger, that is psi is equal to psi naught sine omega t minus kx. So here the wave function was taken in the form of sine function. So here the material particle is moving along the x direction, which will form a sine wave. So this wave function is having the, in terms of sine wave, that is having the position x, momentum p, velocity v and time t. So each and every moving particle, that is here I am going to take electron is the material particle. So electron is having the position x, momentum p, velocity v and time t. So if this electron is moving along the x direction, then what is a wave function was assumed by the Schrodinger as psi is equal to psi naught sine omega t minus kx. So here wave equation, you will get by doing the 2 differentiation, that is by doing the first order as well as second order differentiation with respect to x, then we will get the wave equation for the material particle which is moving. Before that, there is a sound wave. Sound wave is having certain wave equation. Light wave is also having certain wave equation. These similar to that, the each and every wave there is a equation, like sound wave, light wave is having the wave equation. Suppose del square rho 1 by c square dou square rho by dou t square. So this is the equation for the sound wave. Suppose light is also having certain equation. So del square u 1 by c naught square dou square rho by dou t square. So each and every wave there is having some certain wave equation. So that wave equations are there in previously. For now material particle, that is matter wave, is also having certain wave equation. That certain wave equation was derived by the Schrodinger in the year 1926. So how he was derived this equation? By incorporating de Broglie hypothesis and also classical wave equation. So how he was derived the wave equation for the matter wave means by incorporating, means by adding de Broglie wavelength expression and also classical wave equation. So by adding both, he has derived the equation for the matter wave. So for this he has assumed a particle, that is I said, that is electron, which is moving having the velocity v, moving along the x direction. Then the wave function was assumed that psi is equal to psi naught sine omega t minus kx. So here omega is what? Angular frequency. Why it is angular frequency? The electron which is revolving around the nucleus which is revolving around the nucleus will form a wave. So when it is revolving around the nucleus, it having the angular frequency, that is omega. And the time t, here the t is represents time, k is wave vector, x is position. So what is omega? Omega is angular frequency. Next t is what? Time. And k is wave vector as well as propagation vector. So next one is x. So x is a position. Position means here along the x direction the particle is moving. So that's why we are going to take the x. Again here the Schrodinger time independent wave equation. The wave equation should not have the time coordinate, then it is known as time independent wave equation. If the equation having the coordinate time, then it is time dependent. But in our syllabus constraints, we have only time independent but not time dependent. So time independent means simply the equation does not have the time coordinate, then you can say that it is a time independent wave equation. So next one, store the wave function psi is differentiated with respect to x, that is position, by 2 times. So differentiating the equation with respect to 2 times partially, that is not definite integral, this is partial differentiation. So partial differentiation means here with respect to x, that is with respect to x, so you can, the x is only the variable but remaining all are constants. So that is x is a variable, the time t is constant. When it is partial differentiation, whichever you are differentiating with respect, that will be the variable, remaining all constant. So here dou psi by dou x, psi naught, sine will differentiation will be cos omega t minus kx. So when you do the theta is in the form of function, that is omega t minus k. Omega t is, I said, t is constant. So when it is differentiated with partially, x will be the variable, t will be the constant. So when it is constant, the omega t value will be 0. When it is kx, the kx differentiation is minus k. So again differentiate this equation with respect to x, that is dou square psi by dou x square. Cos theta differentiation is minus sin theta. So minus sin omega t minus kx. Again omega t minus kx, again you have the minus k. Previously it is minus k. So minus k is plus k square, and psi naught sin omega t minus kx, again wave function psi. By taking to the LHS side, the equation will becomes to dou square psi by dou x square plus k square psi is equal to 0. So this equation is written from the equation 1. Next, where k is what is the first one? K is known as propagation vector or wave vector. So propagation vector is equal to 2 pi by lambda. So by substituting 2 pi by lambda, what is the equation will becomes dou square psi by dou x square plus 4 pi square lambda square into psi is equal to 0. So next to equation 3, this is known as equation 3. So by incorporating, what is the incorporation here? Classical wave equation as well as de Broglie wavelength. So here I have taken the classical wave equation. So by incorporating classical wave equation and also de Broglie wavelength expression. So what is the de Broglie wavelength expression? Lambda is equal to h by mv. So substituting lambda equal to h by mv, this will becomes 2 dou square psi by dou x square plus 4 pi square 1 by lambda square you have. So 1 by lambda square is known as m square v square by h square into psi is equal to 0. This is the equation number 4. So here we have incorporated de Broglie wavelength expression. Now we are incorporating total energy. So total energy is here. So dou square psi by dou x square. Total energy E is equal to half m v square, that is kinetic energy, plus potential energy is V. So here by taking E here this side, E minus V is equal to half m v square. Multiply both side with m, that is m square v square, and take this 2 this side, that is 2m into E minus V is equal to m square v square. So m square, in place of m square v square, substitute 2m into E minus V, then you will get dou square psi by dou x square 8 pi square. So already m square v square is 2m, 2 into 4 8 pi square m into E minus V by h square. So by substituting in this equation, this value substituting in equation number 3. So by substituting equation number 3, you will get dou square psi by dou x square plus 8 pi square m into E minus V by h square into psi is equal to 0. Here what is the energy equation? The addition of the kinetic energy plus potential energy. So this is what classical wave equation. The classical wave equation is the energy is in the form of kinetic energy as well as potential energy. Kinetic energy is represented by half mv square. Potential energy is represented by capital V, where small v is the velocity, capital V is the potential. So by simplifying this, you will get m square v square value is 2m into E minus V. So by substituting this value, you will get the wave equation. This is what? Wave equation in one dimensional. If the particle is moving along x direction, suppose the particle is moving along y direction, suppose the particle is moving along z direction, the particle is moving along x comma y comma z directions, then the equation will become what? Dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square, plus here instead of 8m, here you will get 2m into E minus V by h cross square into psi is equal to 0. Here h cross is what? H by 2 pi. So here h by 2 pi repeatedly you will get in the quantum mechanics. So instead of h by 2 pi, we will write h cross. H cross is equal to h by 2 pi. So by substituting h cross equal to h by 2 pi, the above equation will becomes to dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 2m into E minus V by h cross square into psi is equal to 0, where the wave function is a function of x comma y comma z. So next, what is here? Dou square psi by dou x square. This is the term, it is known as del square psi. So where here the symbol is known as del square del, and here the square of the del is del square psi, is known as Laplacian operator. The operator is known as Laplacian operator. So by substituting Laplacian operator in this equation, then we will get del square psi plus 2m into E minus V by h cross square into psi is equal to 0. This is what? Schrodinger time independent wave equation. See here, the psi wave function is a function of x comma y comma z, but not time t, and the equation does not have the time coordinate. Then we can say that it is a Schrodinger time independent wave equation. So now, so like sound wave, light wave is having certain wave equation. Now Schrodinger, after discovery of Schrodinger, the wave equation, that is material particle, is also having the wave equation. That wave equation is now matter wave equation. That matter wave equation is del square psi by del square psi plus 2m into E minus V by h cross square into psi is equal to 0. So this is about the Schrodinger time independent wave equation. So how, what is the procedure? First of all, we will revise again. So here a particle is taken the x electron which is moving along x direction. The wave function is assumed by sine wave function. The sine wave function is differentiated with respect to 2x 2 times by incorporating de Broglie hypothesis lambda equal to h by mv, and also classical mechanics wave equation, that is E is equal to kinetic energy plus potential energy. By substituting and also arranging the terms the LHS and RHS, simplifying the equation, then you will get the Schrodinger time independent wave equation. So it is in one dimension, that is in the form of x, in terms of x. If it is 3 dimension, then it is x comma y comma z direction. And here the one operator it is introduced here, that is Laplacian operator, which is equal to del square psi equal to dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square. So this is the derivation for the Schrodinger time independent wave equation. So next topic is physical significance of the wave function. So here in this we have taken the wave function. Actually, what is the wave function here? So wave function has no direct meaning. There, if you square it, that is the square of the wave function has certain meaning. It is a complex quantity and which is described by the moving particle. So moving particle, here it is a material particle, electron, proton and a neutron. At any instant of time, we can find the position and the momentum by using the quantity known as wave function. The wave function does not have the direct meaning. When it is the square of the wave function has some meaning. So here the wave function is explains the motion of microscopic particle. So microscopic particle is for electron, proton and neutron. So psi is a complex quantity it does not have any meaning. So direct psi has no meaning. When it is the square it, then it is having some meaning. So what is the square? That is psi square. Psi is has no meaning, and psi square is represents what? Probability of finding the particle per unit volume. So here volume means x comma y comma z, that is dx dy dz. Within the small region dx dy dz, the product of these dx dy dz is known as volume element. The volume element is represented by d tau. D tau is equal to dx dy dz. So here psi has no meaning, so psi square has meaning. What is the meaning of this? We can find the probability of finding the particle within the volume element, that is d tau. D tau is equal to dx dy and dz. Psi will give the information about the particle behavior, and the probability density function is ranges from 0 to 1. So when it is 0, the particle is absent. When it is 1, the particle is present. So here the probability density function is defined as triple integral. Why it is taken triple integral? Because it is a volume x comma y comma z. So volume is, that is triple integral, that is square of the wave function is psi square d tau. D tau is within the volume element, that is dx dy dz. If it is equal to 1, which is known as normalization condition. If it is equal to 0, that is known as orthogonality function. So when it is orthogonality, the particle is 0. The particle is absent. When it is normal, then the particle is present. Orthogonality condition is probability density function is 0. Normalization condition is probability density function is 1. When it is 1, the particle is present. When it is 0, the particle is absent. So here the wave, and it is a finite value. The wave function is a single value. It is not 2, 3, not 4. It is only single value, finite. Finite means only particular value, that is 0, 1, 2, 3, 4, like this, but not infinity values. It is a finite value and periodic function. Periodic function means constant. The wave function value is constant. And it is the p values are ranges from between 0 to 1. Between 0 to 1, the particle is 0. When it is 0, the particle is absent. When it is 1, the particle is present. So now the wave function has no direct meaning. Square of the wave function has some meaning. When it is square it, then we can find the position of the particle. The wave function is a finite value and periodic and also single value. When p square is equal to 0, that is orthogonality condition. When p square is equal to 1, then it is a normalization condition. When it is normalization condition, the particle presents, and it is 0, there is a absent. So this is about your Schrodinger time independent wave equation and also physical significance of wave function. So next class we will discuss about the application of the Schrodinger wave equation. So by using application of Schrodinger wave equation, we can determine the energy of the material particle. So that will be discussed in the next class. That is, we will see in the next class. We will meet in the next class. Thank you.